Let's jump right in. Welcome back to today's explainer. If you're already familiar with basic networking concepts, well, today we're going to connect those dots into something really incredible. We're taking an in-depth look at enterprise network architecture like you've never seen it before. Okay, I want you to imagine a high-stakes heist. Our main character here, a malicious red hacker request packet. Now, just a second ago, it successfully tricked or, smoothly bypassed the enterprise's very first line of defense, the network firewall. Now, a lot of people might think, well, it's game over. The hacker just walks right in. But actually, this is where the real show begins. The real question is, you made it inside, but where exactly do you go next? Because I promise you, this is absolutely not a straight, open road. It's a highly precise maze, and it's filled with guards and checkpoints. So, to track our hacker packet, we've put together a bit of a route map today. We're going to hit 6 key checkpoints. We'll start with the enterprise route map in NAT, move into security zones like the DMZ, check out traffic distribution with a load balancer, and meet the traffic cop, Nginx. Then we'll try catching malicious intent with a WAF, before wrapping up with a look at a hidden threat.
All right, checkpoint 1, the enterprise roadmap, focusing on NAT.
The reality here is that a true enterprise architecture completely shatters this myth of direct connections. It is not just a simple, straight line from the internet to a firewall and then boom, you're at the web server. No way. It's a highly complex maze. A single packet has to navigate through routers, firewalls, NAT, the DMZ, load balancers, reverse proxies, and then, maybe it finally touches an application. Every single one of these layers has a completely unique, totally critical mission.
And the crucial mechanism making the first part of this maze work is NAT, specifically Destination NAT or DNAT. See, when a hacker launches an attack at a company's public-facing IP address, let's say 2030.113.100, the NAT device instantly strips away that illusion. It secretly swaps the destination of that packet to a private IP that's hidden deep inside the network, something like 10.10.10.10. So the hacker thinks they're in total control of the board, right? But in reality, they're just being led by the nose. They're being forced onto a specific track that the enterprise built just for them.
Which brings us to checkpoint 2, security zones and the DMZ.
So the IP has been translated, but where does the packet actually go next? Listen, there is no way a smart enterprise is letting dangerous, untrusted internet traffic directly touch their internal network full of sensitive data. Enter the DMZ, or the demilitarized zone. You can think of it like a highly scrutinized waiting room. Any service that needs to be open for business, like your web servers, DNS, or mail gateways, gets put right here. The packet can roam around in this specific area, but the very second it tries to cross the line and dig into the internal network, it gets shut down immediately.
And this right here is where network segmentation shows its true power. The firewall isn't just some physical wall, it's an active, intelligent gatekeeper between these security zones. The strategy is actually crystal clear. Allow traffic from the internet into specific services in the DMZ, like, say, TCP port 443, but absolutely 100% deny the internet any direct connection to the internal network. Doing this ensures that even if an external-facing service gets compromised, the enterprise's core crown jewels remain completely safe.
Moving on to checkpoint 3, traffic distribution and the load balancer. Okay, so our hacker packet has successfully snuck into the DMZ, but almost right away it hits a fork in the road. It essentially meets a guard asking, all right, which backend server are you actually supposed to go to? Because massive enterprises dealing with just oceans of traffic, they don't rely on one single web server. They have massive clusters, Web 01, Web 02, Web 03. So here, the load balancer steps in as this brilliant traffic distributor. It's not necessarily asking, are you a hacker? It's asking, where should I send you so the whole system keeps running smoothly?
To figure that out, load balancers usually rely on 3 core logic strategies. First, it can just deal out connections like a deck of cards, using round robin, going in sequence one by one. Or it can be a bit smarter and use least connections, finding whichever server is currently handling the fewest active connections and sending you there. But honestly, the absolute most important feature here is health checks. If Web3 suddenly goes down, the load balancer notices instantly. It ignores that server, ensuring our hacker packet, or any normal customer packet, is never sent to a dead, unresponsive machine.
Let's check out checkpoint 4, the traffic cop, Nginx. After getting sorted out by the load balancer, the packet finally arrives at a server node. But it usually doesn't meet the final application just yet. Instead, it runs into Nginx, which is basically known as the ultimate internal traffic cop.
Nginx perfectly plays the role of a reverse proxy. It actually unpacks the HTTPS request and carefully reads the URL path. So, if it sees you're asking for data via an API, it precisely routes you to the backend API server. If you're just trying to grab an image or a static web page layout, it sends you right to a static file directory. And just like that, under Nginx's flawless direction, our packet is handed off to its exact application destination.
Which brings us to checkpoint 5, catching malicious intent with the WAF. The tension is really building here now.
Because after all that navigating, this little red hacker packet has finally arrived right at the application's front door. But what if the request itself is malicious? Think about it for a second. The packet followed every single network rule perfectly. The firewall let it in, the NAT translated it, the load balancer forwarded it, Nginx routed it, but what if it's hiding a bomb inside? I'm talking about application-level attacks, things like the infamous SQL injection or cross-site scripting. Standard network firewalls are practically blind to these because on the surface they look exactly like a normal harmless web request.
And this is exactly why enterprises deploy a WAF, or a web application firewall. The WAF is the application's ultimate, highly specialized bodyguard. See, it doesn't just care about where you came from, it cares about what you are actually saying. It dissects the packet entirely. It inspects the HTTP headers, looks at the URL parameters, and digs deep, deep into the actual payload. It is literally purpose-built to yank out malicious code that's hiding behind seemingly legitimate requests.
Now, here's where a lot of people get a bit confused, but the distinction is actually pretty brilliant. Think of a standard network firewall as the guy guarding the front door of a building. It only checks your ID and your basic pass, basically asking, are you allowed to enter? A WAF, on the other hand, that acts way more like a polygraph test. It doesn't really care if you have a pass. It looks at your behavior and asks, is what you're holding inside actually malicious? They definitely don't replace each other. They do two entirely different jobs, protecting completely different layers of the enterprise.
All right, our final section, checkpoint 6, the hidden threat. As we wrap this up, let's take a quick step back.
Just look at this incredible journey we just took. A simple-looking red request started all the way out on the vast open internet. It was guided by routers, passed the initial ID check at the first firewall, and then it was forced into a hidden private IP by the NAT. It tiptoed into that isolated DMZ waiting room, got pointed in the exact right direction by the load balancer based on traffic weight, and it was perfectly routed by Nginx. Finally, at the very door of the application, it had to face the ultimate interrogator, the WAF. That right there is the real, complex life of a single packet inside a modern enterprise architecture.
But just when you think the enterprise is this totally impenetrable fortress, I want to leave you with a rather provocative thought. Even if a company deploys the absolute best next-generation firewalls, intrusion prevention systems, and perfectly configures their WAF, what happens if today's hacker packet isn't actually carrying malicious code? What if it's carrying entirely legal, perfectly legitimate employee usernames and passwords that were just bought off the dark web? When malice is perfectly disguised as absolute legitimacy, how on earth does the enterprise spot it? Well, that is a terrifying puzzle, and it's one we are definitely going to have to tackle next time. Thank you so much for joining us for today's Explainer.